Hello everyone, David Ostrowski in this recording. This is Data Structures Algorithm Analysis. In this recording I'm going to be discussing the topic of NP-complete, and I'm going to start off with a reference from Gary Johnson, Computers and Tractability, and I'll be including the book. It's very expansive, however it is the definitive resource on this topic, and this is building on what we learned from chapter 9.7, and this is vital to understand for our final exam. So I want to start off with illustration. In fact, it's the only illustration in this book. Again, there's PDF available. I'll be posting that for your reference. Not that you'll need to read the whole book, but again, it's good to have. So point is to illustrate and motivate one of the topics that we've been talking throughout the entire class. And that is around the fact of the scientific process, what we know about problems that we can solve, we cannot solve. Okay, and here we have a worker just facing his boss. Okay, the boss looks very discerning, and the worker doesn't seem to be very confident, right? So he says, I can't find an efficient algorithm. I guess I'm just too dumb. Okay, and what's the purpose of this? Okay, purpose is to illustrate the predicament of a given problem, nonlinear nature in most cases. That is characteristic of any number of problems. It could be a graph-related problem. As we know, it can be very difficult to optimize. It can also be a scheduling problem, factory line automation. It could be a design problem. What do all these problems have in common? Okay, they all ramp up at an exponential level, and we know that given some of the characteristics of these problems and the algorithms that surround them, at this point I'm sure everyone has an appreciation of exactly what complexity is, okay, and the fact that there are problems among this categorization that transcend, okay, typical issues around mathematical based approaches. Okay, so this speaks to the motivation for using AI based techniques or heuristic based techniques, that simple mathematical approximations cannot be applied in this case. The bigger picture is, as before, we categorize problems as is accomplished in just about any other discipline. And from there is where the research community is supported. So if I have a given problem and I can equate it to, let's say, a graphical search, other people, computer scientists, base researchers, or analytics data scientists, okay, they have pushed the boundaries, solving a problem that has been similarly categorized. So back to our illustration here. I can't find an efficient algorithm. He just can't figure it out. Okay, and this is as you explore the examples. Okay, this is a very realistic scenario. Here he is a little more adamant and says, I can't find an efficient algorithm because no algorithm is possible. Okay, and this is standing with a little more gumption, a little bit more level of confidence. And how would he know that? Okay, he may have done a little bit more research. This speaks to the point of the analysis portion of this course, and specifically how it's defined. Okay, so he may say no algorithm is possible, but again, how do you substantiate this? You need to be able to substantiate this by referencing bodies of work. Okay, so here he has a stronger case. I can't find an efficient algorithm, but neither can all these famous people. Okay, and what are these people behind him? There are any members of the research community. In this is standing on the shoulders of giants. Okay, Alan Turing, Alonzo Church, a lot of these traditional, and these people operated before even the term computer science was formed. They were traditionally mathematicians who were analyzing problems and categorizing them and proposing decades and decades and decades ago, say, hey, this problem cannot be solved by traditional mathematics. It can't be optimized. Okay, and this speaks to the exponential nature of some problems that are become intractable over time, that they can't be solved today, they can't be solved 50 billion years from today, even including the Moore's law and what we understand about the capabilities of computers as they improve in the future. And this is contradictory to what a lot of our current media has claimed. Okay, the AI is going to take over everything. Okay, and solve every single problem in existence. Okay, that's overblown, and if you adhere to these principles. Okay, and it speaks towards the research community. So this is the setup. Okay, this is the setup of the motivation, the understanding, really for the analysis portion of the course. Okay, which I alluded to earlier, but also to the process and some of the techniques, easy versus hard, intractable problems that are unsolvable. Okay, and I'll post some content related to that as well. So with that, I want to move to the next presentation there. I'm just going to talk a little bit more about P and NP and derive some of these points a little bit more. Okay, so NP complete, a rough guide here. And this speaks to the points that were illustrated from our initial chapters. Okay, so here, this is a little bit somewhat of a light introduction. So it's all about time to solve. How do you measure how long a program takes to run when it's given a more difficult problem, such as sorting lists of 10, 20, 30 items. Okay, plot the times. And here it's important to note at this point, what we know about analysis of algorithms, that coefficients have very little influence on this, right? Because we know that over time that relative speeds of computers and relative speeds of architectures and programming languages and so forth, they all come out in a wash. Okay, we know that x as compared to x squared, okay, is substantially smaller. Okay, and when you have this the time, it ramps up exponentially, and it's not all about it really has nothing to do, okay, with our toy problems. Okay, it is about how problems scale. Every problem is easy. Okay, if I'm looking at traveling salesman or searching a graph, if I only have 10 nodes, okay, I can exhaustively search it. Okay, however, when you get into, even with chess, okay, it has an exponentially larger amount of computation time to brute force it, that even today we cannot solve it. And I'll pull the number in another discussion, but this speaks to the point that coefficients wash out. We're looking at polynomial versus non-deterministic polynomial. Okay, so when we say P, we mean it's solved in polynomial time. All right, so let me move forward here. So the N and NP refers to the fact that you're not bound, okay, by the normal way a computer works, just step by step. The N stands for non-deterministic. And this presents a challenge, okay? What do we mean by non-deterministic? Okay, non-deterministic supports the fact that I could have, if I look at among graphical search, that I could have two paths to the same solution. Okay, so that is, if I have a non-deterministic method, in some cases it may be easier to represent a problem, but it represents a lot of complexity in being able to solve the problem resource-wise. So, as I mentioned here, the N can solve a lot of problems in polynomial time, but it's not a supercomputer, just a non-deterministic computer. Okay, so the program's going to take dramatically longer as the program gets harder. The P could be solved quickly on an amazing N computers or in MP. So MP means solved in polynomial time using a non-deterministic method. This includes P problems of polynomial. Okay, so we have MP problems, and that includes P as well as MP. Okay, so the easy problems are in P and MP, but the really hard ones are only in non-deterministic. So they are deemed as MP complete. Okay. So MP complete, they can be solved in polynomial time using only, however, you have to use a non-deterministic method. Okay. It is believed that if anyone could solve an MP complete problem in P time, okay, then all MP complete problems could be solved that way using the same method, and the whole class would cease to exist. So what are we saying here? We're talking about categorizing problems. If I can equate it to, let's say, the traveling sales, or I can put it into a graphical representation, I can have a lot of different solutions outside of just physical, geospatial type of problems. Okay, and if I can equate one problem to another from a solution perspective, then again, if I can solve one, I can solve them all. So, as they point out here, the classic example of an MP complete problem is traveling salesman. And in this case, a brief example that would be: imagine you need to visit 5 cities on your sales tour. Do you know all the distances? What's the shortest round trip? Okay. One obvious solution would again be to check all possibilities, brute force it. Okay. However, and this speaks to my point, as it ramps up, it becomes very difficult to solve it. Okay, so in terms of computation, so that brute force method, that would take factorial time, and we know that factorial becomes very large after a short period of time. It ramps up like exponentially. Okay, it's not linear. So if I have the problem as a 20 city problem, then the 20, if it was solved in 1 second, a 21 city problem would take 21 seconds. Not too bad. Okay, we could still solve that. 22 city, that's still not that too much of a problem. It takes 20 times larger or longer at least. That puts me at 7 minutes, but we can still do that. We can sit here and let a computer crank out that. However, you get to 30 cities, it ramps up so fast it would take you 3 million years. And that speaks to, if it's 3 million years, okay, it might as well be a billion years, right? A trillion years, doesn't matter. Okay, a million is a million, and that's again points to the fact that these problems, the coefficients wash out at certain points. Okay, when you're looking at exponential nature. So there's ways to break this problem down into subproblems. We call it dynamic programming. Okay, The best would still take exponential time. So a city that solves 20 cities in 1 second will solve 30 cities in 10 minutes and 60 in 35,000 years. Okay. So if we had this amazing computer, as I mentioned, it would create copies of itself to check all the possibilities to solve the problem in a relatively shorter period of time. So here, when we mention NP hard, when the problem's method for solution can be turned NP complete, it is said to be NP hard. So that is as hard as any NP problem, and in many cases, it's deemed as even harder. So let me break down some of the concise definitions. I'm going to post this PowerPoint. I think it's crucial to the exam. I'm going to have a couple of questions on this. Okay, this is your motivation for more advanced research. This is the entire culmination and conclusion of this whole idea of the analysis part of it, right? We don't really care too much about a couple loops side by side or whether it's embedded, but we are concerned about these types of problems that fit in the category of incomplete and how we can resolve them. So let's be a little bit more definitive. I'm going to present more content that is going to give you a little bit more insight on this. Okay, so more concise definitions. P is deemed as, in somewhat of a review, but reiterating it, right? The P is the class of decision problems that can be solved in polynomial time by a deterministic Turing machine. What do you mean by a Turing machine? Represents a mathematical means of a programming language. Okay, so I can define a language using a Turing machine, and I can solve any problem. If it's Turing compatible, it's anything I can use a popular language to solve. Okay, and if it's deterministic, that means that there is one and only one way of solving the problem. Okay, so NP is a class of decision problems that can be solved in polynomial times by a non-deterministic Turing machine. Between a non-deterministic and a deterministic Turing machine, okay, they can actually solve the same language. However, you have more flexibility with a non-deterministic machine, but it is more resources, more computational time in many cases, because when you think about it out loud, okay, it is not as efficient, though it may be easy to work with. Okay, if I can have more than one way to solve a problem, then it's going to give me some flexibility, but it is also going to include the need for more research, more resources. Equivalently is the class of problems that can be verified in polynomial time by a deterministic Turing machine. NP hard is the class of decision problems to which all problems in NP can be reduced to in polynomial time by a deterministic Turing machine. NP complete is the intersection of NP hard and NP. Equivalently, NP complete is the class of decision problems in NP to which all problems in NP can be reduced in polynomial time by a deterministic Turing machine. And here's a little chart. Hopefully it'll give you a little bit more context and understanding. Most of the confusion about NP hard is how reductions can be applied. In particular, the last case, you can reduce to a more complicated problem instead of making more sense and decreasing complexity. Determinism is more difficult because it's not as flexible. Okay, and you'll have a greater appreciation of the power of non-determinism if you take the theory of computation, which this class, I assume, would be the prerequisite. So this does not have any logical application and can serve to confuse more than anything. And one can go back to the easy definition and state that NP hard is a very hard set of problems that can exist as harder than NP complete, NP, but not NP complete, in some cases unsolvable. So here's the following problem. So a polynomial-based problem is verified in polynomial, is solvable in polynomial. NP is verified in polynomial. It could be solvable, it may not, but it's definitely more complicated. NP complete It's unknown whether it's solvable in polynomial time, and NP-hard is could be verifiable. We don't know, okay, and it's unknown whether it's solvable, and that's a big question in computer science. Can I solve these non-deterministic problems in polynomial time? If you can do that, then a lot of these gene sequencing problems, flight optimizing flight times, and factory floor scheduling, all these problems the whole world would run much more efficiently. We'd be able to solve diseases easier and so forth. The whole world would change. A lot of people speak to that, but there's no great awards. There's $1 million award to determine this, and no one to this day has been able to solve that. So. And the final point here is be careful with the reductions. So you can only leverage reduction to support less complexity, not more. Okay, you can use it to bump up your categories, not down. So it's used to, it is used to make you feel better about NP-hard. So let's take a look at a non-deterministic algorithm. Here I have a search, and I have my I match to a key, and I do a write, and I identify some of the lines here that are solvable in a polynomial time, right? So one of the approaches here is to separate between polynomial and exponential time algorithms. First objective is combine them collectively, so solve one problem, you can solve all of them. If you cannot write a deterministic algorithm, then you represent it as a non-deterministic algorithm. So with the deterministic, we know clearly how each statement works, and with the non-deterministic, we leave blanks in the algorithm. And that speaks to some of the points here, okay, that here we have specific portions of the code that are going to be identified. So I know it's how to choose a key, but I don't know how the search is going to operate. So so you're going to post that, and you're going to leave that for further research. You're going to kind of put a pin in it and document it as such. And again, these are techniques, the separation between areas of the algorithm, the polynomial and exponential algorithms, okay, to determine what are the most complicated parts, okay. And this speaks to the earlier techniques that we had of making these designations to determine the means of characterizing a solution and also documenting it as such. So we can combine other work and look at related problems that if someone comes up with an efficient means of solving a component of it, then we could bring these problems closer together and progress as a whole with the entire research community. So more to come on this. I got more content. Thanks for listening. See you on the next one. Bye now.